All right, today we're going to talk differentiability again, 3.2, and some options that we have on our calculator, also related to finding derivatives. So what I want you to do is, if you can go to your calculator, what I want you to do on your calculator right now is type f of x into y1, and I want you to type g of x into y2, and we're going to look at those two functions. So just give me like a normal Zoom 6, a standard window. And we're going to look at those two functions laid on top of each other and see and talk a little bit about what we're seeing and what we would assume is happening there. Okay, so I have them, and it's really nice, and you can watch what's happening up here on my graphing calculator as well, because I've got the nice color one up here, and I can easily see if I go to my y equals that the one that's going to be graphed in blue is the absolute value graph, and the one that is graphed in red is the square root graph. And then when I graphed it, I went to a Zoom 6, so that standard window, and they are like the same graph, right, as I look at that. And so if I were to look at both of these, knowing what we know now about where things fail to be differentiable, would you say that both of these fail to be differentiable at 0? Because we see a corner, right? But if I go back and look at the functions themselves, I know this has a corner on it, but this actually, as we look at it, is not. If we look at that, that's not a shape of a corner, right? So the picture itself can be deceiving, is what I'm getting at here. So how are we going to figure this out? G of x is actually differentiable. That is actually not a corner. So here's what I want you to do. We're going to do the zoom in function on our calculator. So if we go to zoom, option 2 says in, and it's going to put this little kind of bug thing on our calculator. Move that up close to the vertex, and if you need to keep moving it each time we go. But if I hit enter, it's just going to kind of zoom in a little bit on this graph. And what I want you to see is, as I zoom in more and more times, look how I can now distinguish the difference between my graphs. They still look the same to me right now. So I'm going to zoom in again. And I'm going to zoom in again. And they start to separate a little bit. I'm going to get my zoom in centered again here, closer to where that vertex is. I'm going to zoom in again. And you see how they kind of start separating? And I'm zooming in. I am zooming in super, super close now. Way down here. Center this up one more time. I'm going to zoom in one more time here. And what you're seeing is that red graph kind of started to look like a curve, doesn't it? And if I were to keep zooming in on that, it actually ends up starting to look even more and more like a line, right? Isn't it kind of flattening out as we get closer and closer and closer to that? I'm going to zoom in one more time here. Look how that now starts looking like a straight line. So as we zoomed in, it started out looking like a V. It then started looking more like a curve, and now it's looking more like a straight line. And so what we're learning here is g of x is actually differentiable, and what you're doing is zooming so far in, you're basically kind of seeing the tangent line that would have been at that location. And notice the blue line, which is our absolute value graph, it never changed. It stayed as a V. It's going to stay as a V, and if it's not differentiable there, that's never going to change. And so that's one of the things we can kind of learn from this little experiment right here, is that if a function is differentiable at a point, if we zoom in close enough, and we had to zoom in really, really far on this one, but if we zoom in close enough, it's going to flatten out to look like a straight line. Because what's happening is we're getting so close that we're basically kind of seeing a tiny little clip of what would be that tangent line at that point. Okay, another thing that we're going to do is learn our calculators can do an approximation for a derivative called a numerical derivative. It is not actually taking the derivative at the exact point, but it's finding 2 points that are like super close to each other and finding the slope of the secant line between those 2 points, which is kind of like our instantaneous rate of change. Remember how we made h go to 0? Well, it's finding two that are so close together that h practically is 0. That's what your calculator is doing. So let's talk about where do we find this on our calculator. You have this numerical derivative option where basically it will take the derivative of a function for you and evaluate it at a given x value using this little format here. I'm going to show you where this is on our calculator and how we get this typed in. And then if you've got one of my older operating systems, we'll have to talk about your slight change to how you would type that in. But if I want to do a derivative on my calculator, let me clear this out here. Okay. To do a derivative on your calculator, we're all going to go to our math option here, which is on the left-hand side. And it's going to be option 8. N derivative or NDER kind of, again, depends on the age of your calculator or the operating system of your calculator. So N derivative, option 8. Mine, I kind of have to arrow through it, so this is going to be a get to know your calculator moment. Let's go ahead and find the derivative of f of x equals x cubed, and we're going to find that at 2. So we're going to find the derivative at 2. How do we type that in? Well, the first thing you're going to do is type in the variable that we are taking the derivative in with respect to. That will always be x. Okay, so you fill in x in that first spot. And then in the parentheses, you type in the function. And our function is x cubed. And then we type where it says, and this is a good thing to learn. We haven't really talked about this yet, but this bar actually does mean we are evaluating. Okay, and we'll use that in our notation as we start writing and evaluating things too. You can show that evaluating it at x equals, and we're supposed to be doing this one at x equals 2. So I type that in here. All right, with that being said, did anyone type that in and it just gave you a parentheses instead of like this little thing right here? If it did, this is how, okay, so if you hit enter, it's going to give you this. If yours just said like n derivative and a parentheses, this is how you type yours in, I'm pretty sure. Whatever the function is, comma, x, comma, the number you are evaluating it at. Okay, that's for my older operating systems, the order you type that in. And you notice that it's actually saying 12.000000001 because it's approximating it. It actually is exactly 12. So what would we put? Well, in AP Calc, what do we round every problem to? How many decimals? 3, right? 3 decimals, always, always, always in AP Calc. Well, if I round that to 3 decimals, it's 12, right? So we would just say the answer is 12. So you have this option. Now, this is a great option. We can use it frequently, but we have to know a little bit about the function itself. I know that x cubed is a continuous function, that it is differentiable at all points along that function. What I want to show you is, let's talk about a function that we know isn't differentiable. We just looked earlier at the absolute value of x, not differentiable at 0, is it? Right? It's got a corner at 0. But if you try your derivative function, your numerical derivative function on your calculator for the absolute value of x, oops, it will tell you that you get an answer at 0. But it's not differentiable there. So this is a wonderful function, can really help us speed up our process on finding numerical derivatives, but we have to kind of understand where its limitations lie and that it will find us a derivative for everything, even if it doesn't exist there, because it's finding that and a point really close next to it. So it's not specifically at 0, it's really close to it. And so that's why it's not understanding that there's not actually a derivative there. Okay, so your calculator does have a little bit of a limitation using this. So you just kind of have to know where those points would be if you're going to do this with a function that might have points that are not differentiable. Any questions on that? No? All right. Last thing I'm leaving you with today is that whole intermediate value theorem. Well, guess what? It's true for derivatives as well. And we've got a little typo in here. If A and B are any 2 points on an interval on which the function is differentiable, then the derivative takes on every value between f prime of A and f prime of B. So again, what is this saying? It says that if our function is differentiable on the interval from A to B, that there exists some C on that interval such that the derivative at C exists somewhere on the interval from f prime of A to f prime of B. Was true for a function and all of its values is true for its derivative and all of its values. Okay. Any questions on that? When you're done getting that in your notes, we are actually going to start your assignment together. So if you'll find wherever you are going to do your assignment. We are going to start on page 115, and we're going to start the first problem together, which is number 39. All right, on number 39, that is the function that they give you at the beginning. Let f of x be this function that's defined as this. A and b are constants. And it asks you, we have two parts to this one. Part A, it says if the function is continuous for all x's, what is the relationship between A and B? So they are handing us a piecewise function, and they're telling us it is continuous. We saw this a couple sections ago, and in order for a piecewise function to be continuous, the limit of each side of those functions as it approaches where it flips between has to be equal, right? So our left and right hand limit as we approach 1 has to be the same to avoid that whole jump discontinuity at 1. Is this all sounding familiar? It's going to look a little different when we get done with this one because we'll have A's and B's in our answer, because we're trying to figure out what A and B would have a relationship, okay? So let's look at the two different sides as we approach 1. The limit as you approach 1 from the left, and the limit as we approach 1 from the left is going to use that first function, because that's where x is less than 1. And we are just talking the limit of the function. So we're not doing a derivative or an instantaneous velocity or anything like that. We're just taking the limit of the function. Well, remember our rules. If I'm taking the limit of this function, can I do direct substitution here? If I sub it in, we don't have any issue, right? So I can sub it in here. The limit from the left is 2. which means we need the limit from the right to also be 2. So let's look at the limit as we approach 1 from the right. And if we approach 1 from the right, we would be using the other function. Again, no problem with doing direct substitution, right? We're not going to get a 0 in the bottom of our fraction or a negative in a radical or anything like that. So I can directly sub in 1. When I directly sub in 1, I get 1 times a plus 1 times b is a plus b, right? And in order for it to be continuous, those two are equal to each other. And that is your relationship between a and b, is that their sum is equal to 2. That's what it's asking you. Questions on that so far? Okay, I'm going to get you started on part B, and then I'm going to leave you to do the rest of the problem yourself. Part B. Part B asks you, find the unique values for A and B. So at the end of part B, and part B takes you a little bit of time here, at the end of part B, you are going to say A equals and B equals, okay? And it says find the unique values for A and B that will make this both continuous and differentiable, okay? Well, in order for it to be continuous, we know this is going to happen. We now need to look at the differentiable part of it. Well, the differentiable part of it means the left and the right hand derivatives need to be equal to each other, yes? So now you're going to do kind of this similar process, but we're going to do our formal definition of the derivative on the left and right of 1. And at 1, they need to be equal to each other. So when we get those two answers, we're going to set them equal to each other. Well, those two answers, again, we're going to have a's in them. So what's going to happen after you do your derivatives is you're going to have another equation with a and b in it. Well, if I have two equations with two variables, I can now do a system of equations to solve for those variables. So you'll come back and use this guy. You'll use the equation at the end of doing your derivatives and do a system of equations to then solve for a and b. Hopefully that makes enough sense that you can get started on part B.